Good morning, everybody. This is College Algebra. I just want to make a few announcements here at the beginning, and then we're going to get started. I want to remind you that you have WebAssign homework due, and this is your last WebAssign homework that's due on December the 6th. And so that will be next Wednesday at the end of the day. There's two homeworks out of section 6.6 and then one homework assignment from section 7.3. The exam 3 review, please be working on that this week. I have a very long review online, and so please pay attention to that and work on the review. The exam, and if you have any questions about the review, you can always come to my online office hours or my on-campus office hours this week, and I will be happy to help you out with the review. Please do that. The exam 3 window starts this Thursday and goes through next Tuesday. And then I have online office hours. I have quite a few online office hours for the rest of the semester. I'll be online tonight from 8 to 9, tomorrow night from 8 to 9, and then again Sunday, Monday, Tuesday, and Wednesday of next week. I will also be on campus, and I didn't write those hours down, and I don't know why I didn't do that, but I will be on campus on November the 29th. That's Wednesday from 4 to 6 p.m. And on November the 30th, which is Thursday, from 9 to 11 a.m. So please come by my office. Remember, my office is in Winship 115K on the North Harris campus, and I'll be happy to help you out with anything you're having trouble with. So those are two great times to come by and actually see me in person and go over some stuff. The final exam window opens next week on the 7th, which is Thursday. So exam 3 window closes on Tuesday. Then there's Wednesday, and then we'll have the final exam window opens on the 7th and runs through Monday the 11th. So please pay attention to that. The final exam review is online. I did post it yesterday, and you have quite a lengthy review, and I have a lot of solutions to the problems. All the answers to all the problems are on there, and a lot of the problems are worked out. And so pay attention to that review. It's in with the other reviews that you've had during the semester, and so that will be a good thing to be looking at and working on going into the final exam. I do want to point out, and I did send an email to this effect yesterday, but there will be a take-home problem for the final exam. And the way that's going to work, that first of all is going to cover the material that we will cover today in class. And you will find as you go through the lecture today that what we're covering in class today, the problems are very lengthy, or they can be very lengthy problems. And it's kind of a long process to walk through. And rather than putting a problem like that on the final exam, I'm going to go ahead and give that problem as a take-home problem. I will assign that, and I put the details in your email yesterday, so pay attention to that email. But I will email everybody out the take-home problem, and you will work on that take-home problem at home. It should be your own work, and then you will email me your solution. It should be a one-page solution. It shouldn't take you more than one page to work the problem. And then you'll email an electronic copy of that back to me, and all the dates on all this are outlined in the email that I sent you yesterday through WebAssign, so pay attention to that email. That take-home problem will be worth 5 points on your final exam. So that's a problem on the final you should not miss. You have lots of time to work on that problem and work through it, and you'll see plenty of examples of that kind of problem in the lecture today. So be kind of watching for that as we go on through this next week, because you'll be getting that take-home problem. All right, so today what I want to do is I want to go back and kind of do a quick review of what we did with systems last time. And then we are going to move on to specifically 3x3 linear systems. Remember the term 3x3 means We are talking about 3 equations and 3 unknowns. We're looking specifically at linear systems, and we want to use a certain type of matrix method to solve those linear systems. It turns out that there are several, actually 3 or 4 different types or different methods for solving a system of equations using a linear system of equations using matrices. We are going to look at one of those. There's like 3 or 4 different methods. We're going to look at one of those methods today. All right. So let's go ahead and get started. Let's first of all look at a quick review from last time. Because I want you to understand the terminology that we use for systems, how this all kind of fits together. And so first of all, remember we have 2 by 2 linear systems. We did a little bit with that. I didn't even assign any homework on that, as I recall. But a 2 by 2 linear system, you're looking at basically where 2 lines intersect, right? And because you're talking about 2 equations that both have graphs that are lines, and when you look at a linear system, the typical type of system has one solution, right? You have 2 intersecting lines. This is called an independent system. So you understand the terminology if you see that somewhere. It's called an independent system, and there's one solution to this system, right? And it's where 2 lines intersect each other. But there are 2 other possibilities for a 2 by 2 linear system. And those occur when you have the 2 lines. Let's see, I'm going to draw a red line on both of these. And then I'm going to draw a blue line on both of these. When the 2 lines are parallel, like that, or when the 2 lines actually end up being the same line. Those are 2 other possibilities. So the second case, where you have parallel lines, right, this is called an inconsistent system. And there's no solution to this system. And you know that algebraically when this happens, when all the variables drop out, when you're trying to solve a system like this, all the variables drop out, and you're left with a false statement. You know, you're left with a statement that looks something maybe like this, 0 equals 3, or something like that. And then finally we have the same line. This is called a dependent system. And there is an infinite number of solutions in this case. Now this terminology is going to come back again when we're talking about 3 by 3 systems today. So that's one reason why I wanted to kind of go back over this again. So there's an infinite number of solutions in this case. And when you solve something like this, algebraically, once again, all the variables drop out. Right? All the variable terms go away. All variable terms drop out. And you're left with a true statement. So a true statement, obviously, would be something like, 0 equals 0 or 4 equals 4 or something like that. You're left with an obviously true statement. Okay, so a 2 by 2 linear system, you had those 3 possibilities. The most common one was the first one, where you just had 2 intersecting lines. And we looked at 2 methods for solving these. We call those algebraic methods for solving. And those were substitution and elimination. The elimination method is sometimes also called addition. So in some book, or if you're looking at videos from somebody else, you may see it referred to as the addition method for solving the system. All right, so we moved on from 2 by 2 linear systems to 2 by 2 nonlinear systems. And that we did spend some time with. This will be on your final exam. Now, the 2 by 2 linear systems I just talked about are not on your final, but 2 by 2 nonlinear systems will be on the final exam. This is not on exam 3, but it will be on your final. And if you look at your review, you'll see that it is on the final exam review. So on the final exam, not on exam 3. All right, so, 2 by 2 nonlinear systems could have been all sorts of different things graphically. So you might have something, like this possibly, where you have one graph is a parabola and the other graph is a line, right? In which case you might have two solutions as a possibility, but a parabola and a line could intersect in one place or could intersect at 0 places also. So that was a possibility that we saw. And I'm not going to draw all the different possibilities here because there was lots of different situations that could have come up. Another possibility would be that if you had a circle, for example, and maybe a hyperbola, right? And a hyperbola might open like this possibly. Not a great drawing, but gives you a good idea. And in that case, there were 4 points of intersection. Right, so lots of different ways, lots of situations graphically in this case. And those were just 2 of those. So I'm just going to put etc. right here because lots of other types of graphs that could have come up. And we looked at the substitution and elimination methods and used those methods to solve this type of system. So one example might look like this: x squared plus y squared equals 5 and y equals 3x minus 5. Now remember that equation x squared plus y squared equals 5, we did talk about that last time, and that's an equation that's in the form x squared plus y squared equals a constant, and that type of graph is a circle centered at 0, 0, and in this case with a radius of square root of 5, right? It's always, the radius is always the square root of k. So the radius is always the square root of k. So in this case, the square root of 5. And then that second graph, well, that one's easy. That's just a line. That's a linear equation. And so we're looking at the places where a circle and a line intersect. You don't absolutely have to know that going into the problem, but it's not a bad idea to know that. Or it's certainly helpful to know that going into a problem. Now, if we want to use substitution here, this is one method we talked about last time. And substitution might be a method that I would think about in this problem. If you use substitution, one equation must be solved for a variable. So it must be in the form y equals or x equals. And if you have an equation that's like that or that's easy to put in that form, then substitution is not a bad method. And in this case, notice the second equation is solved for y. So what I'm doing here is I'm taking x squared plus y squared equals 5, and I'm taking y equals 3x minus 5, and I'm going to substitute y equals 3x minus 5 in place of y right here. And when I do that, I have x squared plus y squared, but in place of y, I write what it would be equal to in the other equation, which is 3x minus 5. And notice when you do that, you're left with an equation that only has one variable. That equation only has x's in it, doesn't have any y's. And so that's what you're trying to get, right? You're trying to get an equation that has no y's or no x's. And in this case, no y's left in this equation. So I can just solve for x. Now we solve for x. And so we multiply all this out, this mess out, and we get 9x squared minus 30x plus 25 equals 5. Now be careful how you square 3x minus 5. Remember, that's 3x minus 5 times 3x minus 5. So this gives me 10x squared minus 30x, and then I subtract 5 and I get plus 20 equals 0. And the nice thing there is that there's a common factor of 10, and then the trinomial you're left with is easily factorable. Factors x minus 2 times x minus 1. Remember, the 10, the constant at the beginning, does not give you any solutions, so you just set the two variable factors equal to 0. And so you end up with x equals 2 and x equals 1 here as x values. And so this means, notice I got two x values. It means I'm going to get 2 points of intersection here, probably, when I look at this graph, right? So when I take x equals 2, I use my equation y equals 3x minus 5, and I substitute 2 in for x, and I get y equals 1. And so there's the point 2, 1 as a point of intersection of these two graphs. And then I do the same thing with x equals 1. I substitute 1 into that equation, 3x minus 5, and I get y equals negative 2. And so I get a second point of intersection at 1, negative 2, which fits in with what we talked about at the beginning, that we had a line and a circle. And so it makes sense that we might get 2 points of intersection. All right, so this kind of goes back over the substitution method for solving an equation. We would not have thought about elimination in this case because if you look at the two original equations, there were no like terms between the two equations. But when you get like terms between the two equations, then you could, I'm going to need to insert a second page here real quick. If you bear with me. There we go. All right. But when there are like terms between the two equations, then elimination all of a sudden becomes a possibility. So in this example, we have the equation x squared plus y squared equals 26. And based on what we've talked about, that's a circle. And then we have the equation 3x squared plus 25y squared equals 100. And because the coefficients of the x squared and the y squared are not the same in this problem, this graph is going to be an ellipse. So remember that when you have an equation in the form x squared plus y squared equals k, you get a circle, right? When you can make the coefficients of both the x squared and the y squared be equal to 1, like I just did, then it's going to be a circle. If you can't do that, then the equation x squared plus ax squared plus by squared equals k, right, where the x squared and the y squared coefficients can't be made to be 1s, both 1s at the same time, then you get an ellipse. So if you think about a circle and ellipse, there could actually be as many as 4 points of intersection between these two graphs. All right, notice that there are like terms. Notice there are like terms between the equations. And so let's use, in this case, let's use elimination, right? When you get like terms like this, then elimination all of a sudden becomes a possibility. So I take my two equations, x squared plus y squared equals 26, and 3x squared plus 25y squared equals 100, and I decide which variable I'm going to eliminate, because there's x squareds in both equations and y squareds in both equations, so I could eliminate either variable. So I'm going to eliminate x. And so to eliminate x, I need the coefficients of the x squares to be opposites of each other. So I take the first equation, and to make the coefficients of the x squares opposites, I'm going to multiply the first equation by negative 3. When I do that, the first equation becomes negative 3x squared minus 3y squared equals negative 78. Negative 3 times 26 is negative 78. And remember, you have to multiply negative 3 by every term in that equation. The second equation, I just leave it alone. And now I add the two equations together. So we add equations. And when you do that, and when the coefficients of the squares are opposites, when you add them, what's going to happen? The x squares are going to go away, and you're just left with 22y squared equals 22. When you add you're just adding columns together here. And notice this works out really well. We get y squared equals 1, and so y is equal to plus or minus 1. All right, so now I take my first equation. It doesn't matter which one you take at this point, by the way. So I'll take the first equation, x squared plus y squared equals 26, and I use y equals 1 and y equals negative 1. When y equals 1, you get x squared plus 1 squared equals 26. So you get x squared plus 1 equals 26. X squared equals 25. X is plus or minus 5. Don't forget, when you're taking the square root there at the end, you have to use both a positive and a negative 5 as solutions. And so notice, when I used y equals 1, I got x to be plus or minus 5. And so that's actually 2 points of intersection. I get negative 5, 1. X is negative 5 and y is 1. And I get positive 5, 1. X is positive 5 and y is 1. So you get 2 points of intersection there. Now, notice that when you take our equation x squared plus y squared equals negative 26 and you use y equals negative 1, notice the exact same thing is going to happen. I'm not going to go through the rest of this, but notice you're squaring negative 1 now, and it's going to be the same thing. And so you're going to end up with plus or minus 5 here as well. And so you get 2 more points of intersection. You get negative 5, negative 1, and negative 5, and positive 5, negative 1. And so you end up with 4 points of intersection for these two graphs. And so now we've gone through substitution and elimination. All right, so now what we're going to do is we're going to move on to 3x3 linear systems. And again, I'm going to need an extra page here, an extra page or two. So if you'll excuse me while I move some pages around. I've got some stuff prepared ahead of time here, so I needed to do this. All right, so let's look at 3x3 linear systems. That's our next stop. And this is our last stop at looking at systems of equations, is we're going to look at 3x3 linear systems. Now, a 3x3 linear system means there's 3 variables. So a linear equation in 3 variables might look like this. X plus 2y plus 3z equals 6. Since you're talking about an equation in 3 variables, this is actually a 3-dimensional graph. We are not going to look at the graphs of these equations, but the graph is a plane in 3 dimensions. So if you just think about or picture the floor in the room you're currently standing in, or a wall, or the ceiling, or if you take a piece of paper and hold it at an angle out in space like that, those are all examples of pieces of planes that are cutting in 3 dimensions. And so if we look at this graph right here, x plus 2y plus 3z equals 6, we're actually getting a plane in 3 dimensions. If you wanted to picture a 3-dimensional system on your paper, because your paper is a 2-dimensional sheet, right? But you can actually draw this if you draw it like this. Technically, what happens is you have the x-axis and the y-axis, and then the z-axis is coming out from the wall or coming straight out of your paper. But we can't draw it that way, and so you draw it at an angle like this. And then you can use dashed lines like so. This is common in Calculus 3, by the way, where we're looking at graphs like this. And then typically, in this case, the x-axis comes out from the wall. This is the y-axis, and then this is the z-axis like this. Now, do not worry about trying to sketch these kinds of graphs. Absolutely not. That's not what we're talking about doing. We are talking about looking at some algebraic methods for solving these systems, but we're not going to look at a graphical method at all. All right, so we have this equation x plus 2y plus 3z equals 6. Its graph is a plane. So if we looked at several other equations. So let's say we have negative x minus 4y. Let's say, let's not say minus 4y. Let's just say plus y equals, or I'm sorry, I'll get it right here. Minus z equals negative 4. And then finally, 2x plus 3y minus 5z equals 10. Right? That would be a typical system, a typical 3x3 linear system. All three graphs are planes, and what we're looking at is we're trying to find where these three planes intersect. So solving this system means looking at where the three planes intersect each other. Now the point where they intersect is called an ordered triple. Not an ordered pair, because now we have three variables, so it's called an ordered triple, and we write the ordered triple alphabetically with the x-coordinate, the y-coordinate, and then the z-coordinate like that. And so the solution to a system like this is an ordered triple. Now, just like we've seen with linear systems in 2 dimensions, you could have some special situations here. You could have all the variables drop out algebraically, and when that happens, you have either a dependent or an inconsistent system. In other words, it could be an infinite number of solutions, could be no solution at all to the system. And if we had some time, we would look graphically at this, but we don't really have a lot of time here at the end of the semester. And so we are not going to be looking graphically at those three situations and trying to figure out when they occur and how to write them. It's a little bit more complicated than with 2x2 systems. And I'll just talk briefly about how you know when you get one of those special cases later as we finish this up. Now, what we will do is we are going to use an augmented matrix to solve this system. So now a matrix is simply an array of numbers and that we usually put in a big set of brackets like this. And the augmented matrix for this particular system, so notice I have brackets like this. The augmented matrix for this particular system looks like this. The first row of numbers, this is called the row, first row right here, and it's 1, 2, 3, and 6. The second row of numbers is -1, 1, -1, and -4. And then the third row is 2, 3, -5, and 10. So now notice that those numbers just simply come from the coefficients of the equations in the original system. This is the first equation right here. So each row represents an equation. So this is called row 1 right here. And the second equation is row 2. And then the third equation is row 3. And we're going to refer to those as row 1, row 2, and row 3. We are going to usually, the way I'm going to abbreviate this is I'm going to abbreviate this R1, R2, and R3 like that. All right, now the columns, notice, the columns are the variables. So the first column, so these are the columns right here, and the first column are the x's. And the second column is the y's, and the third column is the z's. This is called an augmented matrix because there is another column here that is the coefficient or the constants sitting on the other side of the equal sign. And so these are the constants right here. And this is called the augmented matrix for this system. All right, so now the idea is this, is that we want to take an augmented matrix like this one right here, and we want to try to figure out a way to rewrite it in what the textbook refers to as row echelon form, or sometimes I just abbreviate that as triangular form. All right, so now what the heck does that mean? So let me copy down our matrix right here. So I'm going to copy that and pull it over to the next page. what we want to do is we want to figure out a way. We want to figure out a way to rewrite this matrix in what the textbook calls our textbook calls row echelon form, or you might just see this referred to as triangular form. So what is row echelon or triangular form? What does that look like? Now I'm going to put a dot, dot, dot here, because what we're going to spend the lecture doing is trying to figure out what that dot, dot, dot means. How do we go from that matrix to this matrix? And why is this last matrix a nice form to get is the question. So let's say my first row is still 1, 2, 3, 6, but the second row is now 0, 1, negative 2, 3, and then the last row is 0, 0, 1, negative 3, like this. This is what we call row echelon form or triangular form. And with row echelon form or triangular form, notice that you get these zeros right here, and these zeros kind of form a triangle. And because they form that triangle, then we might call it triangular form. Notice also that the diagonal, these numbers right here, are all ones. Now that's not absolutely essential to this method that those all be ones. That's common to see that. We're going to look at that at the end. But do they have to all be ones? No, they don't. If you just had those 3 zeros in those spots, you could still solve that system. All right, now how does this work? Why does that form help us to solve the system? Well, if you look at the system that this is generated from this last matrix, the system looks like this. It's x plus 2y plus 3z equals 6. That's just our first equation. But the second row, notice the first number in the second row, the first entry is a 0. That means there's no x in this second equation. And so you get y minus 2z equals 3. And then in the last row, notice there's 2 zeros at the beginning, the 0 in the x column and the 0 in the y column. So it means there's no x or y. And so you're just left with z equals negative 3. So that's the system that comes from that triangular form right there. And that system can be solved, this can be solved using what we call back substitution. So using back substitution, all you're saying is if I take that last row and solve for z, which it already is, right? So I get z equals negative 3. And then I take the next row, y minus 2z equals 3, and I substitute z equals negative 3. Notice that that will allow me to find y. So you get y minus 2 times negative 3 equals 3. So you get y plus 6 equals 3, or y equals negative 3 also. So now you have z equals negative 3 and y equals negative 3. And then you take the first equation and you take both z, which you have found from the very beginning, and y, and substitute both of those in, and then you can find x. So notice what you're doing is you're kind of, back substitution means you're substituting and then going back and substituting again, right? So you have x plus 2 times negative 3 plus 3 times negative 3 equals 6. So you have x minus 6 minus 9 equals 6. It's x minus 15 equals 6. X equals 21. And so you get x equals 21. And so the solution to the system is going to be the ordered triple 21, negative 3, negative 3. Right, that ordered triple makes this last matrix a true statement. And then if that last matrix was equivalent to the one at the very beginning, then they would have the same solution to the system. They'd be the same solution, and so we would have solved the original system also. So our question now, it comes down to this. What's going on right here? Let's see. Let me put a color in here. What's going on right here with those three dots? How do we do that, right? So that's the question, is how do you take a matrix and rewrite it in this row echelon or triangular form? And so that's what we want to talk about today, all right, is that process. And I didn't leave myself nearly enough pages here in the middle, so we want to put a few more pages and stick them in here. I need some blank pages because I had some problems that are worked out already, so or not worked out, but the problem has started. I have to be careful how I pick these problems so that they turn out. I'm going to try to avoid fractions as answers just because I don't want to get hung up in all the arithmetic and everything. And so how do you go from an augmented matrix to an augmented matrix in triangular form or row echelon form? So how do you do that? That's the question. All right, so there are basically three things that you're allowed to do to a matrix that means that the resulting matrix is equivalent to the first one. First thing is you are always allowed to interchange two rows. You're allowed to do that, which makes sense because all a row represents is an equation. So you're allowed to interchange any two rows. All right, so the way you would write that is like this. So let's actually look at an example of that. Let's say we have this matrix right here. 3, 2, 1, negative 4, 1, negative 6, 7, 8, and negative 5, 1, negative 2, 6, like this. Now, it is going to be to our advantage if we can do this, is we would like this entry right here, the very first entry in the matrix, we would like that to be a 1. Whoops. We would like this first entry to be equal to 1. Now, if it's not equal to 1, it's not a disaster. But if you can make it a 1 easily, then doing that would be a good thing. And now notice it's not a 1 in this matrix, but the second row does start with a 1. So if we literally just take row 1 and row 2 and we interchange them, and that's the way I write that row operation right there, then all I'm doing is interchanging those two rows. I'm just literally flipping them around. Row 3 just stays put. All I'm doing is interchanging rows 1 and 2. Easy row operation. All I did is flip those two rows right there. Right, so that's what this first row operation means to do, is interchanging rows like that. Sometimes that's to your advantage. And this is one situation where it would be to your advantage. Second row operation is you're always allowed to multiply any row by a constant. You're always allowed to multiply any row by a constant. All right, so let's look at an example of that situation. So let's say I have this matrix like here. So let's say the first one starts with a 1. It doesn't really matter, but let's say I have 1, 2, negative 3, 4, and then I have 0, 3, 5, negative 6, and then I have 0, 5, negative 2, 4, like that. And let's say that that's my augmented matrix. And I would really like, in this case, is I would really like this 5 right here, this entry, I would like that to be a multiple of the entry right above it. I would like this entry to be a multiple of 3, the entry that's right above it. And 5 is not a multiple of 3. Remember, the multiples of 3 are 3, 6, 9, 12, and so on. So how could I make that number a multiple of the 3? Well, I could just simply multiply 5 by 3. But that means I have to multiply the entire row by 3. And so the way you write this row operation is, what we're going to do is we're going to take row 3 and we're going to multiply it by 3. And then we're going to put that in place of what row 3 was. And that's the way we're going to write this. So we're going to take row 3, multiply it by 3, and then put that in place of where row 3 was. And that's the way I write that row operation down. So under this row operation, row 1 doesn't change. Row 2 does not change. But row 3 does, and all you're doing here is multiplying that last row by 3. Every entry by 3. That's all we did. So I get 0, 15, negative 6, 12, because I multiplied every entry in that row by 3. And that's the way you'd write that row operation. All right, so there's our second row operation. Multiply any row by a constant. And I gave you a situation where that might be a convenient thing to do. Also, an easy row operation. All right, the third row operation is a little bit trickier. And it goes like this. We're always allowed to replace any row with the sum of itself and a multiple of another row. Oh my gosh. All right, so let's see how that would work and what that means here. We're actually looking at a situation here where that would be to our advantage to do that. So let's say that these are our entries. 1, negative 2, 3, 5, 3, 1, 4, 6, and negative 2, 8, 5, negative 3. All right, there's our matrix, our augmented matrix. I would really like this entry and this entry both to be zeros. But I would like both of these entries to equal 0 because we're headed towards triangular form. I want zeros in those two spots right there. So how am I going to do that? How am I going to get zeros? Well, I could use a multiple of row 1 to do this. Use a multiple of row 1 to accomplish. So how does that work? Well, we're using this third row operation right here to do that. This third row operation, replace any row with the sum of itself and another row, and a multiple of another row. So what I'm going to do here is I'm going to use a multiple of row 1 to get a 0 where that 3 is. And the way I'm going to do that is I'm just going to simply take row 1 and I'm going to multiply it by negative 3. So negative 3 times row 1. And then I am going to add that to row 2. And I am putting that in place of row 2. Right, and that's my row operation right there. Okay, so let's see. So how does that work? Now notice the way I wrote the row operation is which row is changing. Well, it's row 2 that's changing. So row 1 I don't touch. It stays the same. But I am using a multiple of row 1 to change row 2. And under this row operation, row 3 does not change either. It's only row 2 that's changing in this row operation. What am I doing? I'm taking every entry in row 1 and I'm multiplying it by -3 and I'm adding it to what's in row 2. Right? So I'm taking -3 times this row 1 and I'm going to add it to every entry in row 2. So -3, so -3 times right here row 1. And then I'm going to add to row 2. So -3 times row 1, -3 times 1 is -3, added to 3 gives me 0. -3 times -2 is 6, added to 1 and you get 7. -3 times 3 is -9, added to 4 and you get -5. And then -3 times 5 is -15, added to 6 and you get -9. There's lots of arithmetic you're doing here, and so you have to take this slow so that you don't make an arithmetic mistake. That's the big enemy in these problems. It's lots and lots of arithmetic, and quite a bit of it that you have to kind of do mentally. All right, and notice that gave me a 0 in that first row in that entry. Now, it also like a 0 in entry where the -2 is also. And so I use row 1 to do that also. So now I take, to get that multiple there, and so that when they add I get 0, I would like that entry to be a 2. So what I'm going to do is I'm going to take 2 times row 1, and I'm going to add that to row 3. So I add to row 3 and under this row operation. So what am I doing? I'm taking 2 times row 1, I'm adding it to row 3, and I'm putting it in place of row 3. Right, so when I do that, row 1 stays put, row 2 stays put. The only row that's changing under this row operation is row 3. And what am I doing? I'm taking 2 times every entry in row 1, and I'm adding it to the corresponding entry in row 3. So when I do that, I get 2 times 1 is 2, added to -2 is 0. 2 times -2 is -4, added to 8, I get 4. 2 times 3 is 6, added to 5, and I get 11. And then 2 times 5 is 10, added to -3, and I get 7. And I now have zeros in those 2 spots right there. Now this is the trickiest of the row operations, but it's the one you're going to need the most often. And so we want to, kind of practice that and pay attention to that as we're doing it. So I've gone through that row operation twice on this problem right here. All right, so now what we're going to do is we're going to piece all this together, and we are going to actually solve some systems using this method. All right, so here's our first matrix right here. So I've got a couple of first system of equations written out right here. So I've got several systems of equations, and we're going to walk through these steps to actually solve this system. And these problems take up some space, so if you're working these, please kind of allow yourself some room. All right, so the augmented matrix, first of all, that we're going to use is this right here. You have 1, -1, 1, 8. And if you've gotten this far in the video, or for those of you who are with me live, I think you can see where how the augmented matrix is related to the original matrix. And so there's our augmented matrix for this system. All right, and so the idea is we want this to be in row echelon form. So we want zeros in these 3 spots. Right here. We need zeros in those spots. And to do that, so we need zeros in those spots. We're going to do that in this order. We're going to get that 0 first. That's our first one. We're going to get that 0 second. We're going to use row 1 to do that. And then we're going to get that 0 third. And we're going to use row 2 to do that. So we're going to use row 1. Use row 1 always for zeros in spots. Not a very mathematical term, but in spots 1 and 2. And then we're going to use row 2 for the 0 in spot 3. Always, 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 that's what we're going to do. It's best to just always do these in the same order. There are different orders, but if you do it in the same order, you have a lot less chance of getting lost in the problem. Now notice we do have a 0 in that very first entry. Yay, that's a good thing. So since we have a 1, not a 0, we have a 1 in that very first entry. And so that's something that is good to have, and is this 1 right here in that very first entry. All right, so how do I use a multiple of row 1 to get a 0 in spot number 1? Well, what I do is I'm going to take, and I want you to write these row operations out in every step. I'm going to take negative 2 times row 1, and I'm going to add it to row 2, and I'm going to put that in place of row 2. And so this is my new matrix right here, my equivalent matrix. The only row that's changing is row 2. So what I usually do is I write down the other rows so I'm not tempted to try to change one of those. The only row that's changing here is row 2. And I take negative 2 times every entry in row 1 and I add it to the entry in row 2. So I'm multiplying each one of these by negative 2, and then I'm adding to that row right there. So it's times negative 2 and then add. So negative 2 times 1 is negative 2, added to 2 is 0. Negative 2 times negative 1 is 2, added to 3 and I get 5. Negative 2 times 1 is negative 2, added to negative 1 is negative 3. And negative 2 times 8 is negative 16, add to negative 2 and you get negative 18. Now, everything else is changing too. That does not matter. What matters is getting that 0 in that entry. That's what we need. All right, so now we're on our way. So now we need to get a 0 where the 3 is. That's spot 2. We need a 0 in that spot right there. So to get a 0 in that spot, I'm going to take row 1 and I'm going to multiply it by negative 3. So I'm going to multiply by negative 3 in row 1, and then I'm going to add it to row 3 in this case. And so that row operation looks like this. Right? We're going to take negative 3 times row 1. We're going to add it to row 3, and we're putting that in place of row 3. So here is rows 1 and 2. Those do not change, remember, under this row operation. It's only row 3 that's going to change under this row operation right here. So row 3, I take negative 3 times everything in row 1, and I add it to what's in row 3. So negative 3 times 1 is negative 3, added to 3, and I get 0. Yay, that's what I wanted. Negative 3 times negative 1 is 3, added to negative 2, and I get 1. Negative 3 times 1 is negative 3, added to negative 9, and I get negative 12. And then negative 3 times 8 is negative 24, added to 9, and I get negative 15. Okay, so, and you know, it's never a bad idea to go back over your arithmetic in all of these problems and make sure that what you're doing is actually, what you wrote is exactly what you wanted to do with the arithmetic there. All right, so now we've gotten zeros in those two entries, in spots 1 and spot 2. And now I'm focused on spot 3, and I need a 0 in that spot. Remember, this is spot 3 right here, and I need a 0 right there. I would like that number to be a multiple of what's right above it. We practiced this earlier. I would like this entry to be a multiple of the one right above it. This needs to be a multiple right here of 5. That's spot 3. And then I can get a 0 there. And so what I'm going to do here is I'm simply going to take a little bit of a sidestep, and I'm just going to change row 3 only by multiplying row 3 by negative 5. So negative 5 times row 3, and I'm just going to put that in place of row 3. So this is an easier row operation. And so the first two rows don't change here. And all I'm doing is taking row 3 and I'm just multiplying everything by negative 5. So 0, you don't lose the 0 there. And then you get -5, and then 60, and then 75. Sometimes those numbers get a little bit big. That's okay. Don't panic when that happens. All right, and what did I want here? Again, remember, I wanted this spot 3 to be a multiple of the number right above it. And so now it is a multiple. And now I can use my row operation, the more complicated row operation here to get that 0. What am I going to do here? I'm just simply going to take row 2 and directly add it to row 3 and put it in place of row 3. All I'm doing, that's technically the multiple of row 2 you're using here is 1. You're taking row 2 and multiplying it by 1. And when you do this, let's see what I get. Rows 1 and 2 stay put. They don't change. Nothing happens to them. But I'm taking row 2 and I'm adding it to row 3. Technically, it's 1 times row 2 and adding it to row 3. So notice I don't lose that 0 at the very beginning because 1 times 0 is 0. Added to 0, I get 0. And then 5 added to -5 is 0. That's what I wanted. -3 added to 60 is 57. And then -18 added to 75 is 57. Like that. And now this form is in, or this matrix now is in what I call triangular form. Now it is not technically in row echelon form because I don't have 1s down the diagonal. I have a 1 in the first entry, but not in the other 2 entries. You could go through and put 1s in those diagonals if you wanted to. I'm just not going to get hung up on that at all. I'm just going to get the matrix into triangular form like I have, and then use back substitution to solve the system. Now, what are the equations that are represented by this last matrix? Well, the equations look like this. Excuse me. Had to sneeze there, excuse me. So you have x minus y plus z equals 8 is the first row. Notice the first row is not going to change through this whole process. The second row is 5y minus 3z equals -18. And then the last row is just 57z equals 57. And so notice I can use back substitution to solve this system. All right, so now use back substitution to solve the system. All right, so that last equation, 57z equals 57, I can solve for z and I get z equals 1. Just divide both sides by 57. Now, will you always get a nice integer like that? Absolutely not. But I am only going to kind of center on problems where you're getting integer answers here. I just do not want to get hung up on the fraction arithmetic here. And so I'm going to tend to focus on those kinds of solutions at the ends of these problems, just so you know. Next row, you have 5y minus 3z equals -18. You substitute z equals 1 into this form. And so you get 5y minus 3 times 1 equals -18. And then, so that's -3. So you add 3 and you get 5y equals -15. Divide by 5 and you get y equals -3. And then finally, you take the very first row, and that gives me the equation x minus y plus z equals 8. And you go ahead and substitute 1 and -3 in there. So you have x minus -3, be careful here, plus 1 equals 8. So that's x plus 3 plus 1. That's x plus 5. Well, hardly, right? It's hardly x plus 5. That's x plus 3 plus 1 is x plus 4. That's better. And so you get x is equal to 4. And so I get the ordered triple solution to this system. I'm going to write this at the top here. The solution to this system is going to be the ordered triple 4, -3, 1. Now, obviously, you could check that easily. That ordered triple is supposed to make all three of those equations true. It's the only ordered triple that makes all three of those equations true. Graphically, what we've just found is the point out in the space where those three planes intersected each other, which don't worry about that at all. Instead, simply worry about the fact that we found this ordered triple algebraically using an augmented matrix, and that ordered triple, that set of x, y, and z values is the only one that exists that makes all three of those equations a true statement. And obviously, you could check this to verify that. So I'm just going to do that with one equation. If I check the last equation, 3x minus 2y minus 9z equals 9, right, then this would be 3 times 4 minus 2 times negative 3 minus 9 times 1 is supposed to equal 9, right? And so that gives me 12 plus 6 minus 9 equals 9, and sure enough, I get 9 equals 9, right? So it makes it true. And you would do that with all three equations. All right. All right, so there's a worked out problem, worked it out completely. And so now I'm going to just work through a couple of other problems and for some examples here, and then show you what your homework is for this. And the homework is actually in these notes. All right, so here's, first thing you do is you write down the augmented matrix that goes with the system. Please be neat. Notice that things have got to line up. And if things don't line up very well when you write it down, when you're dealing with matrices like this, then you can really make it's easy to make just careless errors. All right, so there's my augmented matrix. Now the first thing is, remember, we talked about is it's nice if you can get that entry right there to be a 1. It's not a 1 like this, but I do have a 1 that's in the entry right below it in row 2. And so what I need to do is swap those out. And so that's my first row operation in this problem, is I take row 1 and row 2 and I simply interchange them. Remember, I want you to write down the instructions here for each line so that I know what row operation you're using in any particular step. And so I flip those 2 rows. That's all I did in this step. Everything else stays the same. All right, so now I have a 1 in that entry. And now what do I need to do? Remember, I've got spots 1, 2, and 3. So here's spot 1, here's spot 2, here's spot 3. I need zeros in those 3 in that order. I use row 1 for spots 1 and 2, and I use row 2 for spot 3. All right, so the matrix, or the multiple I use of row 1 is -4 times row 1, and I'm going to add that to row 2, and I'm going to put that in place of row 2. Now we could combine these first 2 row operations in one step if we wanted to. I don't really like to do that just because I think sometimes students kind of, it is kind of sort of an overwhelming process because there's a lot of steps to these, and so it's easy to get lost. So I like to spread it out over 2 steps. So what am I doing? I'm taking that first row and I'm multiplying everything by -4, and then I'm adding it to row 2. So -4 times 1, and by the way, I'm going to write row 3 down here because row 3 I'm not changing in this step, and row 1 I'm not changing. So I wrote both of those rows down. All right, so -4 times 1 is -4, added to 4 and is 0. -4 times 2 is -8, add to -1 and I get -9. -4 times -1 is 4, added to 2 and I get 6. And then -4 times -1 is 4, added to 11 and I get 15. Boom. All right, so I got 0 in that first entry, so that's good. So then now the next thing, now I use, what am I going to do? I'm going to take row 1 and I'm going to multiply it by -2 now. And I'm going to add that to row 3 and then add like that. So I'm taking -4 times row 1, I'm adding it to row 3, and I'm putting it in place of row 3. So I'm trying to be neat here, trying to not write too big so I can try to get this all on one page. It's nice to see the whole process on one page if you can do it. All right, so -2 times Notice, by the way, I also wrote down rows 1 and 2 first because those aren't changing in this row operation. So negative 2 times 1 is negative 2. Add it to 2 and I get 0. Negative 2 times 2 is negative 4. Add it to 2 and I get negative 2. Negative 2 times negative 1 is 2. Add it to negative 3 and I get negative 1. And then negative 2 times negative 1 is 2. Add it to negative 1 and I get 1. Always go back through the arithmetic. Make sure that every step that you didn't make any careless arithmetic mistakes. All right, so I got zeros in spots 1 and 2. So now I'm going to try to get a 0 in spot 3. And remember that I would really like that entry right there to be a multiple of the number right above it. I want that negative 2 to be a multiple of negative 9. So what I'm going to do in this step is I'm simply going to multiply this last row by negative 9. And so in other words, I'm going to take negative 9 times row 3, and I'm just going to put it in place of row 3. And that will give me a multiple where I need it. Right? You need a multiple in that spot. So rows 1 and 2 I don't mess with. By the way, notice there is a common factor in row 2 of 3. You could have divided that out to make the number smaller if you'd wanted to. I'm not really going to do that, but you could have. So negative 9 times everything in row 3, so that makes that an 18 right there. And so notice that number is now a multiple of the number right above it. Negative 9 times negative 1 is 9. Negative 9 times 1 is negative 9. There we go. And now finally, I can finish this by taking row 2 and multiplying it by 2 and then adding to row 3. So I'm taking 2 times row 2, adding it to row 3, putting that in place of row 3. So when I do this, I get the first row, don't mess with it. So I write it down. Second row, don't mess with it. So I write it down. Third row is the one I'm changing. Under this row operation, I'm taking 2 times everything in row 2 and adding it to row 3. So 0 added to 0 is 0. Negative 18 added to 18 is 0. 2 times 6 is 12. Added to 9 is 21. And then 2 times 15 is 30. Added to negative 9, and I get 21. All right, and so now I've got this system in triangular form. And the system that I've got left, I always write the system down, is x plus 2y minus z equals negative 1. And then I have no x in the second equation. I have negative 9y plus 6z equals 15. And then finally 21z equals 21. It's not in row echelon form because the diagonals are not all ones, but it is in triangular form. I can solve this system. So I'm going to go over along the side here, and I'm going to solve. I have 21z equals 21, so z is equal to 1. And then I take the second row. This was row 3 right here. I say take the second row. The second equation. I have negative 9y plus 6z equals 15. And I substitute z equals 1 here. So I get negative 9y plus 6 equals 15. Negative 9y equals 9. Y is negative 1. So I have z equals 1. I have y equals negative 1. And then I take the first row, the first equation, x plus 2y minus z equals negative 1. And I substitute again, this time for y and z. And I have x plus 2 times negative 1 minus 1 equals negative 1. So you have x minus 2 minus 1 equals negative 1. X minus 3 equals negative 1. X is equal to 2. And so there's my ordered triple solution. I get 2, negative 1, 1 for my ordered triple solution. Never a bad idea to check that and make sure that that actually works out and that you get the true statement for all 3 equations, that ordered triple makes all 3 equations a true statement. All right, so there's the process for a second problem. All right, and I always think it's good to see several. Now, what I do going into this one right here, what I would strongly recommend you do is if you're watching this video later, in a recorded version of this video, what I would do is I'd stop the video at this point, take this matrix right here, and see if you can solve this one yourself, going through the steps that we talked about. Now I'm going to go ahead and write out the solution, but I would hope that you'd stop the video at this point and see how you do with this. It's important that you be able to walk through this process. And remember, this is the process that I'm going to put as a take-home problem for your final exam. I'm going to give you a matrix or a system like this and ask you to take the augmented matrix that's associated with the system and write it in triangular form and then solve the system at the end using back substitution. So I'm definitely going to give you a problem exactly like these that's going to be on your final. It's going to be a 5-point problem. All right, so first thing I'd want to do is I would clearly want to see if I could get that 1 up there, and so I'm going to interchange rows 1 and 2 again on this problem. By the way, if you can't interchange rows 1 and 2, if you can't get a 1 in that situation, then you just need to make sure that spots 2 and 3 are the multiples of what's in row 1. And so you may need to do something at the beginning to get those numbers to be multiples. That's all you need. But if they're 1s, they're automatically, if that first entry is a 1, it's automatically a multiple. Right? So the first row is now 1, 1, negative 1, 4. Second row is 2, 1, 0, 2. Last row is 3, 2, 1, 0. Just interchange rows 1 and 2. All right, and so now notice that these numbers are both multiples of 1, right? That's what you needed, is both of those numbers to be multiples of that first one. And if that first entry is a 1, then they're always multiples. That's why we'd like it to be a 1. If it's not a 1, then you've got to just multiply rows 2 and 3 by a constant to force them to be multiples. Not a big deal, but it does just take an extra step. All right, so what am I going to do? What's my first row operation? I'm going to take row 1 and multiply by negative 2. So you have negative 2 times row 1 added to row 2. Put that in place of row 2. And in this problem, I think what I'm going to do is I'm going to go ahead and take, and I'm going to add right there. And then I'm going to do the same thing. I'm going to multiply that first one by first row by negative 3 and add it to row 3. So I'm going to go ahead and combine those two row operations in this step. So you have negative 3 times row 1 added to row 3. Put it in place of row 3. Just in the interest of time and space here more than anything else. So row 1, don't mess with it. Row 2. All right, so I take negative 2 times everything in row 1 and add it to row 2. So negative 2 times 1 is negative 2, added to 2 is 0. Negative 2 times 1 is negative 2, added to 1 is negative 1. Negative 2 times negative 2 is 2, added to 0 is 2. Don't worry that we lost that 0 because we don't need a 0 in that spot. Negative 2 times 4 is negative 8, added to 2, and you get negative 6. Do the same thing with row 3, but now I'm multiplying by negative 3. So negative 3 times 1 is negative 3. Added to 3 is 0. Negative 3 times 1 is negative 3. Added to 2 is negative 1. Negative 3 times negative 1 is 3. Added to 1, and I get 4. And then finally, negative 3 times 4 is negative 12. Added to 0, and I get negative 12. All right, so now I've got zeros in spots 1 and 2. Now, I do need this number to be a multiple, which it is, but it's not. They're not opposites. It would be nice if they were opposites. And that way I could just not worry about multiplying it. You know, you could actually do that. I think I'll back off on that. It is a multiple, so I'm going to just go ahead and do that directly. And so negative 1 is a multiple of itself, certainly. So how am I going to get a 0 in that last spot? Well, I'm going to take row 2 and multiply it by -1 and add it to row 3. So this is -1 times row 2, added to row 3, put it in place of row 3. And so I have 1, 1, -1, 4, and then 0, -1, 2, -6. And then the last row, I have 0, -1 times -1 is 1, added to -1 is 0. -1 times 2 is -2, added to 4 is 2. -1 times -6 is 6, added to -12 is -6. And there is my matrix in triangular form like that. And so now I'm ready to solve the system. All right, so I kind of went through that pretty quickly, but hopefully now that that's the third example, that all kind of makes a little bit more sense. So now I write down my matrix, that's the resulting matrix. I'm sorry, I write down my system that results from this matrix. Say it right. So I get this system. And so then I use back substitution to solve this. So 2z equals -6 gives me z equals -3. And then I take -y plus 2z equals -6. I substitute z equals -3. I get -y plus 2 times -3 equals -6. That's -y minus 6 equals -6. I add 6 and I get 0, so you just get y equals 0. You get -y equals 0, but that still gives you y equals 0. And then I take my first equation, x plus y minus z equals 4, and I substitute, and I get 0 for y, -3 for z. Be careful, it's subtracting there. So you end up with x plus 3 equals 4, or x equals 1. And so my ordered triple solution is 1, 0, -3. And so that's a solution to the system right here. That's the ordered triple that makes all three equations a true statement. All right, now your homework for this material, I'm not going to assign problems out of the textbook. Instead, I just have a nice little homework assignment on the last 3 pages of these notes, just for you to walk through all these different things that we've talked about. So problem 1 is just simply writing an augmented matrix for a system. Problems 2, 3, and 4 are all practicing row operations and writing out the correct matrix there. Problem 5 is taking a matrix that's in triangular form and solving the resulting system that you get from that using back substitution. And then finally, problem 6 is actually going through the whole process of writing out and solving a system using this. And by the way, I use this term, I never used this term before. Gaussian elimination is the process that we're using where we're going through using these row operations to get zeros. So it's called Gaussian elimination. So don't panic if you see that term somewhere. All it means is using these row operations that we've been talking about. So these last 3 pages, these last 6 problems are a good review of all the material that we've talked about. And all of these are kind of fair game, certainly for an exam question. This last problem is going to be the take-home problem, or not this specific problem, but it's going to be a problem like this one. All right, so that's our lecture for the day. This is really the last lecture of the semester, pretty much. We will, if there's any need, I will post a lecture later next week to kind of tie up loose ends here, but I don't think I really need to do that because we've got through a lot of examples today. So does anybody who's watching live right now, Amber, Doug, do you guys have any questions? You usually don't.
I'm good over here, Professor.
And Amber, I'm not sure if you're still there, but so if there's no questions, then everybody have a great day, a great last week. Please let me know how I can help you prepare for exam 3 and your final exam. So you have 2 busy weeks here for our class. So be working on all these reviews and let me know how I can help you out. Have a great day.